Hello, everybody. I'm I'm sorry to be not able to be with you today, but I'll try to give you this presentation as best as I can. This talk is about a simulation of 140 kilowatt battery charger for UPS. So what are we talking about? UPS is an energy supplier for loads, for critical loads during grid blackout, and convert the battery voltage 400 volts to the IDC bus of the UPS 800 volts at the maximum power of 130 kilowatt. This work has been done for Schneider Electric, and you can find details in the publication below. What is the constraint of the architecture? We dispose of 3 potential DC bus. All the potential is regulated by the PFC. The battery current is up to 360 amps discharge, and the switching frequency has to be higher than 16 kilohertz to suppress audible noise for old men. But actually, it's old men by UPS. We use a best-in-class IGBT, but it's 15 years ago. So switching frequency is set to 18 kilohertz. We implement a double Bucker boost topology, which is a 3-level differential topology. It means that the battery is connected between the plus potential and the negative potential. And we implement a common mode filter for EMC issue. And the positive leg is the negative leg is out of phase relative to the positive phase with an interleaving of 180 degree. I've put the parameters of the component in the presentation, so we can see that the parameters. Here we can see the waveform, the voltage waveform, and we can see the switching potential of positive leg, which is between 0 and 400 volts, and the negative ones. We can see interleaving between the two voltage, and the resultant, the differential voltage, is between 40 and 80 volts, depending on the duty cycle, and the apparent frequencies. The apparent frequency is twice the switching frequency, effect of interleaving. The current of both potential and positive and negative pole is shown here. I've measured the negative current positive to be able to put in the view of SIMBA and to compare easily with the positive one. We can see that the high frequency ripple is in opposite side of the positive one, and in permanent way the average value of each is equals to the battery voltage in yellow. But the battery voltage is very high, 360 amps, so we want share this current between more than one semiconductor. So we decided to implement 4 legs interleaving for each converter, positive and negative one. So we begin to simulate the positive one only with 4 legs and 90-degree interleaving between each legs. The waveform have been will be improved. We'll see that. The resistor loaded is divided by 2 because we have only half of the DC bus. And each leg have its own inductance, sum up in the filtering capacitors. Here we can see the 4 voltage switching voltage. We can see the interleaving of each voltage. And for the current, we can see here that each current leg is fourth of the battery leg, and the ripple is interleaving. The high frequency ripple is interleaving between each current legs. So the resultant, the sum of all this current, lead to a very clean current in the battery. But each leg works independently as a two-level one, and the ripple in the inductors is kept constant, proportional to DC voltage divided by L. So the switching losses in the semiconductors tends to be constant because the high frequency ripple is dominant in the switching losses. As for the inductance losses, so we cannot decrease the inductance volume as the decrease of is DC current because of this high frequency ripple. And the number of legs increase, so the total switching losses, the total losses increase. And it's not satisfactory, it's not good. So we try to use coupling to improve the waveform. Each leg works, we add 2 coil transformer in each phase and coupling the transformer in a cyclic way to have the combination of switching voltage in each phase in order to have each leg working as a 1/4 converter. It means that the apparent frequency in each leg is 4 times the switching frequency, and the high frequency ripple in each leg is divided by 4. At the cost of adding 4 transformer, but we can use instead of this transformer a unique intercell transformer. But in simulation to begin, it's better to separate 2 functions between filtering and coupling to better understand the working. We can see here that the coupling of the transformer is inverse. In the couplers in SIMBA, the coefficient Km is negative, is put with a negative minus. And we can see the coefficient coupling of the transformer is very high. It means that it's only a transformer. There is no leakage, or approximately no leakage. The inverse coupling leads to cancel the DC flux in the coupler. It's what we want. So here is the result. We can see the current waveform and the high frequency ripple in each current leg is divided by 8. by 60, because the frequency, the apparent frequencies imposed to the inductor is n times the apparent frequencies, and so on. Thus, each leg works as a quarter converter. Inductance could be divided because here the high frequency ripple is very low and it's not an optimized way. So we can divide inductance by 10 to reduce the volume of inductance and use only the leakage of intercell coupler we see after to filter the converter. By dividing this inductance, dynamics of the converter is better. So we can see here the difference. The relative high frequency ripple is higher, but it remains acceptable, and the resultant ripple in the battery current is a little bit higher, but it's not the end, because we can build a complete converter with 4 3-level legs. It means 9-level converters. Each legs switches the DC voltage divided by 2 and the battery current divided by 4. Inductances and coupler are integrated into one intercell transformer, one transformer with 8 coils, coupling together with magnetic cores. The coupling coefficient is around 99% for leakage of 10 microarray. It's a good coupling, so we limit the high frequency effect of leakage in the coil, so we limit the losses. And the coupling sign depends on current leg signs, because it's not all the same between positive and negative part of the converter. So we can see here the converter in SIMBA. There is a lot of components, so we have to put them in a logical way to be able to verify, to check faults and errors in the implementation of this converter. I've tried to do it as best as I can. So we have on the left the switching part of the converter, positive and negative switching legs, and on the right the filtering part with ICT and capacitor, differential capacitor filtering just on the left, on the right, and so on. So waveform, not parameters. We have no inductance, no more inductance, but we have the coefficient, the coupling coefficient of the transformer, which is 99%. Here is the waveform. We can see that 8 leg currents is approximately equals. The DC current is well shared between all the legs, and we can see less high frequency ripple because we have 8 legs and not 4. So the interleaving effect is improved. As for the battery current, a little zoom on the leg currents, and we can see the superposition, the sum of ripple, common mode ripple and differential mode ripple, which is not at the same frequencies. This is the effect of interleaving. The differential mode ripple is related to the magnetizing inductance of intercell transformer. Thanks a lot, Emmanuel, for so great color in your software. It's very beautiful, amazing. Okay, after that we have to control the current in the battery. We have made the simulation in open loop without any defect, and all the leg currents are equals. In simulation, each leg is driven by the same duty cycle, so a closed loop control by a proportional integral is obvious. We have just to measure the battery current and add a proportional PI controller, so on. We can see on the left a PI controller with its parameters on the right, and it works well. We can see that if the dynamic of the loop is not so high, all the current remains equals. But to do that, someone observe perhaps that the resistance in series with the inductance and with the intercell transformer is very high because it's 1 ohm. In this way, the dynamic of sharing of equilibrate the current is very high, and in simulation we can see a good sharing. But it's not really the resistance. The real resistance is around 10 milliohms. So the dynamic is equalizing current is very low, and if the inductances could easily handle overcurrent because it's relatively low constraints relative to the DC current of each leg. It's some amps relative to 60 amps, and the inductance is made to deal with DC flux. ICT is not like that. It's very sensitive to the different current because the leg current is the DC flux made by leg current in the coil, in the core, the magnetic cores, is made to cancel each other. And if we have a little difference between current, it made a DC flux driven by magnetizing inductance, and this one is very high, so saturation is very quick. Donc we have to control each current. The way we choose to control this is to separate common mode and differential mode. The common mode is control the sum of all the current and control the first leg, and we calculate the difference between this current, the current of leg 1, and other legs, and control this difference to 0 for each other legs. So the topology is like that. We can see at the up of the slide the common mode controller, and below the differential mode controller. And we can see here the filtered current of each leg. In yellow, it's the one, the first current, and the other current is very identical, with which each current tries to lead the first current with certain dynamics set by the PI controller. Okay, but this slight difference lead to a big difference in positive voltage relative to negative voltage at the output and the output of the converter, and lead to high frequency ripple at the switching frequencies in the battery current. To deal with that, the solution may be to decrease common mode dynamics, or to control each output voltage to ground by imbricated control loop. One loop for the positive voltage, one loop for the negative voltage, and a current loop to imbricated to control the battery count. But the time is over, and thanks you for your attention. Thanks a lot for your attention, and feel free to contact me if you have any question. Bye.